how do we teach an AI to predict the future and plan its actions, not just accurately, but in a fraction of a second?
We're diving into the secret weapon that promises, well, a 10 times speed up for robotic planning.
Welcome back to the Deep Dive. We synthesize complex research and boil it down to the essential insights you need.
And our sources today come from Artificial Intelligence, Papers and Concepts, which is curated by Dr. Satya Malik.
And as your guides through all this, I should probably mention the slight irony that we, your hosts, are powered by the very technologies we're talking about.
Yeah, right. But setting our own algorithms aside, our mission today is really all about efficiency.
It is. We're focused on a critical bottleneck in robotic control, gradient-based planning, or GBP.
A technique that has always, in theory, been faster and more scalable than other methods. The problem.
It just hasn't worked well in the real world.
Exactly. We need to understand why it failed and how new research is finally closing that performance gap.
And promising that incredible speed you mentioned. So let's start with the heart of this puzzle. The world model. What is it? Why is it so important for planning?
Okay, so think of a world model, a WM, as the agent's internal physics engine. It's like its own little simulator of reality.
And its job is pretty straightforward.
Very. Given a current situation and an action you want to take, it has to predict what happens next, the next situation.
And this isn't simple data, right? For a modern robot, the input could be, a messy camera feed.
Absolutely. And to handle that, WMs rely on what are called latent spaces. They use a really powerful encoder. In this research, it was the Dino V2 visual encoder to map that raw visual input
into a cleaner abstract representation.
Right, a much lower dimensional latent state. It captures the essence of the environment and just ignores all the noise.
And that's where the planning actually happens.
That's it. Once the world is reduced to this clean code, planning becomes, well, it becomes an optimization problem.
You're just trying to find the best sequence of actions.
The optimal sequence that minimizes the distance between where you are now and where you want to be, all inside that abstract space.
Okay, so let's look at how we find that optimal sequence. There are two main approaches in AI planning, right?
That's right. First, you have search-based methods. The gold standard there is something called the cross-entropy method, or CEM.
And CEM is reliable.
Oh, it's robust. Very reliable, but it is incredibly computationally demanding. It works by just generating and testing thousands of random action sequences.
Performing these rollouts.
Yeah, these rollouts, and then it iteratively refines the best ones it finds.
That sounds incredibly slow, especially if you have to do this every single time the robot wants to move.
It is. CEM scales very poorly. It requires constant slow rollouts and just a massive amounts of sampling, which brings us to the alternative, gradient-based planning, GBP.
And the promise of GBP is just, well, revolutionary.
It is. Because the world model is built to be differentiable, meaning we can calculate the exact mathematical influence of an action GBP, can skip that whole costly sampling phase.
It just uses gradient descent.
Just like training a neural network, it optimizes the whole action sequence end to end. It should be efficient and scalable.
But, and this is the big question, if so great on paper, why has it always lagged behind CEM and performance? Why do researchers keep getting stuck?
It all comes down to a fundamental misalignment, what the paper calls the train-test gap.
Okay.
See, world models are trained on these huge, fixed data sets of clean, perfect, expert trajectories. They learn to predict the next step if the agent is acting flawlessly. It's called teacher forcing.
So the model is only learning to drive on a perfect paved highway.
Precisely. But then, at test time, you use it for planning. And the objective completely shifts. The planner is now trying to solve this optimization problem, which means it has to explore.
It has to try weird things.
It tests non-expert, intermediate, sometimes just plain bad action sequences to find the best path. And immediately, the model is forced to drive off-road.
And since it only trained on the highway,
Its predictions just break down, almost instantly.
This deep dive is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. Okay, so we've set up this objective mismatch. Let's dig into what happens when the model is forced off-road. What are the fatal flaws that stop GBP from working?
The first flaw is the creation of what are called out-of-distribution, or OD, states.
Out of distribution.
Right. When the gradient descent algorithm explores these intermediate action sequences, it rapidly pushes the latent state into parts of the world model's internal map that it just never saw during training.
These sequences are almost adversarial to what the model knows.
They are. And
Yeah.
when the world model hits one of these OD states, what do you think happens?
It starts guessing.
It starts guessing. The prediction error gets really high. And because planning means you're rolling the model forward over a long time, say 25 actions into the future, those small initial errors don't just add up.
They compound.
They compound exponentially. One bad guess leads to a completely unreliable state in the next step, and the entire plan becomes useless.
It's like a GPS trained only in Paris trying to navigate a dirt road in the Rockies. It'll just confidently tell you to drive off a cliff.
That's a perfect analogy.
Yeah.
And that's the compounding error problem. The second major flaw isn't about accuracy, it's about the optimization itself. It's what they call the rugged optimization landscape.
A rugged landscape. So if optimization is like trying to find the lowest valley, what does that look like?
It's a terrible place for an algorithm to be. It's full of icy patches, hidden bumps, and deep, misleading crevasses.
In technical terms.
In technical terms, it means the loss surface, the map that guides the planner, has tons of poorer local minima or these wide, flat regions where the gradient is basically zero.
So the algorithm starts going downhill, but it either gets stuck in a tiny, non-optimal valley or it just gets stranded on a plateau and has no idea which way to go.
Exactly. And this makes gradient-based planning brittle. The optimization is just highly unstable. So to make it practical, the researchers had to solve both problems, stabilize the model in those ode regions, and smooth out that rugged terrain.
Which brings us to the two solutions in the paper. Let's start with the one for the compounding errors. Online world modeling, or OWM?
Right. OWM is brilliant because it directly tackles the OD problem. It iteratively teaches the world model about the exact kinds of trajectories the planner is likely to explore. It forces the model to face its own mistakes.
Okay, walk us through that. How does it face its mistakes?
It uses a true dynamic simulator. So first you do a GBP run with your current world model. That gives you a sequence of predicted actions that the planner thinks are best.
Okay.
Then, and this is the key, instead of just moving on, the algorithm executes that entire sequence of actions in the ground truth simulator.
Ah, so you use the real world, or a high-fidelity sim, to check the planner's weird exploratory ideas.
Yes. And this execution generates a corrected trajectory. It's a sequence of the actual states that resulted from the planner's actions, including all those strange off-road OD states where the model failed before.
Oh, wait, I have a question here. The whole point of a world model is to avoid using the slow, expensive simulator, right? Doesn't this negate the benefit?
That's a great question, and it's about the design. OWM isn't done continuously during every planning step. It's done iteratively during training or fine-tuning.
Ah, so it's an investment.
It's an investment. You use the expensive simulator periodically to generate this really high-quality, diverse data that expands the WM's training distribution. You're basically using the planner itself to find the hardest training examples.
So you're collecting targeted data to patch the holes in the model's knowledge.
Precisely. And by doing this repeatedly, the world model gets fine-tuned to cover the specific regions of the latent space that GBP wants to explore. It's actually very similar to a technique called DAGGER, dataset aggregation, but applied here to the world model itself.
Okay, so OWM fixes the unreliable predictions, but we still have that treacherous, rugged, lost landscape to deal with.
And that's the job of the second solution, adversarial world modeling, or AWM.
Right. AWM is all about smoothing out that terrain to make optimization stable.
It does that using adversarial training. It explicitly seeks out and corrects the regions where the model is most vulnerable to instability.
How does that work? Are we training a second network to attack the first one?
No, it's actually much simpler. During the fine-tuning, AWM applies these tiny calculated perturbations, little nudges, to the latent state or the action input.
And these nudges are designed to do what?
They're designed to maximally increase the world model's prediction loss. They are specifically trying to find the worst possible input for the model at any given point.
So the algorithm is actively finding the weakest points in the model's understanding and then forcing it to train on them until they're no longer weak spots.
You've got it. Fine-tuning the model on these really challenging, perturbed trajectories, it has this regularizing effect. It forces a much smoother transition between states.
Which means that the loss landscape gets smoothed out.
The landscape becomes gentler, making it way easier for gradient descent to find the optimal path without getting stuck. And they even visualize this, showing that AWM creates a much broader basin around the optimal solution for tasks like push-T. It's a huge win for stability.
And they were smart about efficiency here too, right?
Very. They use the fast gradient sign method, FGSM, to generate these perturbations. They found it gave them comparable performance improvements to stronger, slower methods, but was much, much faster to run during training. A very pragmatic choice.
All right, let's get to the bottom line, the performance. You have these two methods. They combine AWM with a good optimizer like Atom. How did it stack up against the gold standard, CEM?
The results were definitive. The combination of AWM and Atom for GBP successfully matched and in many cases exceeded the success rate of the slow traditional CEM. On tasks like point maze and wall navigation, AWM with Atom GBP actually outperformed CEM. They proved that with the right training, GBP could be truly reliable.
And they had hard evidence that they closed that train test gap.
Absolutely. They showed a plot where initially the model's prediction error was way higher on planning trajectories than on expert data. After fine-tuning with OWM or AWM, that gap either vanished or completely reversed.
So the model was now better at handling the chaos of planning than just replaying expert moves.
Exactly. It was trained for the job it was actually being asked to do.
Okay, so stability problem solved. Now, for the part that really matters for real-world robots, the speed. Matching CEM is great, but why should a roboticist really care?
They should care about the cost. AWM with Atom GBP matches the performance, but it does so with an order of magnitude, a 10 times reduction in computation time compared to CEM.
10 times faster. That is a game changer.
It is. In the real world, an agent has to replan constantly. If your planning takes 100 milliseconds with CEM, you can only react so fast. If you get that same quality plan in 10 milliseconds with robust GBP, your robot can act faster, handle dynamic environments, and just be deployed in places where speed is critical.
And it's important to remember this wasn't on some toy model. They used DynoWM, which leverages the Dyno V2 visual encoder.
Right, which proves these methods work even with rich, high-fidelity visual features. The results are immediately applicable to state-of-the-art systems.
What's really fascinating here is the paradigm shift. We're moving past just training a world model to be accurate on clean data.
We're now explicitly training it to be robust during the actual optimization. We're anticipating that the planner is going to explore and try to break the model, and we're forcing the model to learn from those failures before they can even happen.
It's that focus on optimization time robustness.
That unlocks the speed and reliability of gradient-based planning. It's a fundamental change in how we should think about training these models.
A phenomenal advance. It proves that planning doesn't have to be slow if we just train our models smarter. And if you're excited by this blend of computer vision and planning, you can get started in the field right now. We urge you to enroll in opencv.org University to get started in computer vision and AI.
Thank you for joining us as we took this deep dive into how preparing for failure can make AI plans so much faster.
Don't forget to subscribe for more expert analysis of complex topics. We'll see you next time.